Good evening, everybody, and thank you for coming. First of all, I would like to express my gratitude to Professor Olaf Slemaker, who gave me the opportunity to come from France to Vancouver to share with you some ideas concerning the ongoing environmental changes in the Arctic. And the good thing with this lecture series is that you will be provided with different perspectives from various speakers on various environments and objects, like the Arctic today, but also the hot deserts, the coastlines, the mountains, and the rivers. No doubt that the balance between, for instance, the climatic and the human drivers won't be the same for the Arctic and for some tropical densely populated coastlines. So today, no surprise if I put much emphasis on the climatic driver in the Arctic. This does not mean at all that, to me, at a global scale, it is the most important. To me, the human impact, the mismanagement, are something very important in many places in the world. You know surely that there is an international group on climate change called IPCC, which every 6 years or so publishes a report concerning climate change. You will see that I am a bit critical about IPCC. It doesn't mean that I am a climate skeptic, but I will try and provide you with a balanced appreciation of what's going on in the Arctic without hiding you the uncertainties. I know that Olaf Slemaker, in his introductory talk, evoked already the uncertainties. I think what is interesting is also to see that many questions are still open. I won't give you a view pretending that everything is clear now. I think many things are unclear, in fact. As Olaf said, I am a geomorphologist, and I have worked mainly in the Arctic, in North Labrador, in East Canada, and Spitsbergen, and Lapland, and a little in the Antarctic Peninsula. So my talk will be partly based on this field experience in polar regions. It will be also based on many exchanges I have had with international colleagues, not only geographers, but also biologists, glaciologists, or paleoclimatologists. Interdisciplinary exchanges are, to me, as crucial as international ones. And last, this talk will be based also on a knowledge of the international literature, especially the review I had the opportunity to do together with a Russian geophysicist, Oleg Anisimov, when I had the opportunity to contribute to a book edited by Olaf Slemaker on geomorphology and global environmental change, which was published last year at the Cambridge University Press. So let's start with the slides. We'll look at the circumarctic belt as a global change hotspot, mostly, for sure, from the climatic point of view, but we'll show that even in the Arctic, some of the environmental impacts at a local scale are driven by human action. So what I suggest is that we start with the evocation of the drivers. Then we will examine together the environmental responses to global change of the Arctic regions and their socio-economic implications. We will mainly focus on sea ice retreat, permafrost thawing, and continental ice melting. And I'd like to conclude by focusing my presentation on some projections and uncertainties concerning the future trajectory of changes in the Arctic, in polar regions in general, with some global implications. So let's start with the climatic drivers. The main thing is that the Arctic is particularly sensitive to climate change due to its latitudinal position and to the abundance of snow and ice, which are prone to melting. Concerning the ice, you have first the huge, though very thin, sea ice cover around the North Pole, covering the Arctic Ocean. Second, you have the continental glaciers, with special reference to the Greenland ice sheet, which is 3 kilometers thick in the middle and contains 9% of the total amount of continental ice. And thirdly, you have on the right the hidden ice, I mean the permafrost ice, the ground ice, which covers much space in Arctic and subarctic regions. Permafrost occupies 50% of Canada, 60% of Russia, and 85% of Alaska. So the Arctic regions have undergone a more drastic climate warming than the rest of the world. You can see this pronounced warming trend in red on the map at the bottom left of the slide, and also on the curve on the right, where you can see that the average temperature change during last century is at plus 2 degrees in the Arctic, whereas the global average is at 0.7 degrees. And there are some places in the Arctic, parts of Alaska and Siberia, where temperature rise has been higher at plus 4 and even 5, and these are real hotspots of climate warming. Even the permafrost ice, 20 meters below the ground surface, is warmer now. There were some exceptions until the mid-1990s. For instance, in East Canada, permafrost was still cooling, but since the mid-1990s, it seems from recent studies that permafrost temperature started to rise even in such places which were exceptions before. As you may know, during the same 100 years, the sea level rose by 20 centimeters or so, which means plus 2 millimeters per year, possibly plus 3 since the 1990s, although there is a debate about this increase, the reality of this increase, because the method used to measure the sea level rise changed from tide gauge records to satellite altimetry measurements, and some people say that it's because of the change of methods that there is what is an apparent increase in sea level, and some others say that it's a reality linked to the warming which accelerated in the very end of the 20th century. Now we will examine the anthropogenic changes, which are, even in the Arctic, potentially conducive to environmental impacts. Of course, it is difficult to call the Arctic a global change hotspot because of human activity. The total population of this huge circumarctic belt is only 4 million, which is nothing compared to human concentrations of temperate and tropical regions. However, at a local scale, some drastic changes have happened. First of all, with the exception of the Inuit of Arctic Canada and Greenland, the native communities represent now a very small percentage of the population. For instance, in Russia, you see on the left the map of the communities. In Russia, you have 65 different native population, including the Chukchi, who are represented in the middle of the slide by the woman with her baby. All these native communities are very, very small minorities in Russia. They represent less than 5% of total population. Moreover, in Russia, as in Canada and Greenland, drastic changes in activities and ways of life have happened, from a nomadic lifestyle to the development of fixed settlements. This is, of course, part of a global trend which is characterized by a concentration of populations, either in villages or in big cities, with especially in northern Russia, as you can see here on the right. Most of the biggest concentration are due to industrial development associated to extraction of fossil fuels and mineral resources. In Russia, 65% of oil and 93% of natural gas are produced in permafrost regions, and both the Russian and American Arctic have seen a huge development of transportation networks and industrial facilities. Also, tourism development, on the left on the slide, is also part of another global trend which has potential and real, as we will see, environmental impacts. So now let's have a look at the responses of the Arctic environments to the various global change drivers. And let's start with the sea ice retreat. This is one of the less controversial topics. Undoubtedly, the sea ice has retreated at least by 15% since the 1950s. And this trend is particularly pronounced in summer, especially recent summers. You can see here the striking 2007 minimum, but it is part of a trend which started in the 1990s, resulting in an accelerated retreat rate of sea ice, 3% per decade. However, there is a hot debate concerning the causes of this accelerated sea ice loss. For some scientists, it is part of a general trend associated with global warming. For others, this accelerated sea ice loss is completely independent of the warming trend, but it is linked to unusual wind patterns which flushed an unusual amount of ice out of the Arctic. So the interannual variability of weather conditions could be a basic fundamental driver of what's going on in the Arctic sea ice. Well, the second explanation seems, the weather conditions, seems to be more convincing to some scientists who emphasize precisely the high interannual variability of the weather conditions in the Arctic, and who note that following the 2007 minimum, the sea ice loss stopped when weather conditions changed. As you can see at the end of the graph, the sea ice loss stopped, and there is even in 2009 a slightly increase in the surface covered by sea ice. Another debate deals with the amount of the contemporary thinning of the Arctic sea ice. Many scientists think that there has been a 40% decrease in sea ice thickness since the 1950s, but others point out the unreliability of thickness comparisons at fixed points when the pack ice is moving, as are the thickest and oldest parts of the pack ice. And they also emphasize the difficulty to extract the long-term trend because of the high interannual variability in sea ice thickness, which you can see on the right. And last, some say that the comparison is biased, for one compares the present state of the sea ice cover to the one of the 1950s, which was the coldest period within the 20th century. So it's easy to show that the retreat now is very important compared to this period where the sea ice was much more important than, for instance, in the 1930s and 40s. On the other hand, many Inuit population have observed a pronounced sea ice thinning at many sites, and some of them point out some difficulties for traveling because the sea ice is not as safe at some places as before. And there were some accidents at the end, especially at the end of the 20th century. Another consequence of the sea ice retreat, which is also currently very often emphasized, is that the realm of the Arctic fauna is more and more restricted, with special reference to the emblematic polar bear and walrus. However, this should not be overestimated compared to the terrible damages to the Arctic and Antarctic faunas due to man action. Let's think of the decline of the blue whale, the fur seal, and the Antarctic krill due to hunting and overfishing. Another consequence of the sea ice retreat is the opening of the Arctic passages, who had been forced after many unsuccessful tries of a lot of explorers. They've been forced by two Scandinavian explorers, Nordenskjöld for the Northeast Passage at the end of the 19th century, and Amundsen for the Northwest at the beginning of the 20s. As you know, the Northeast Passage, north of Russia, is nowadays currently used by ships and provides new opportunities to exploit the Siberian mineral resources and to develop tourism, but in the same time, of course, it provokes additional cultural shocks for Siberian native communities, of which some try and maintain their traditional way of life. As to the opening of the Northwest Passage in Arctic America, it provides both opportunities and concerns, and I'm sure you know better than me what's going on concerning the Northwest Passage. Of course, the opening of the passage provides opportunities for the population of the remote settlements of the high Arctic, who are less isolated as previously, opportunities for companies to exploit new oil resources, and in the same time, there is much concern about the potential ecological disaster that would represent an oil spill within the Canadian archipelago, where the oil would be trapped and stay much longer than what happened along the Pacific coast with the Exxon Valdez oil spill. Sea ice retreat has also induced new geopolitical concerns related to the property of the Arctic Ocean and its resources, with, for instance, claims from Russia and Norway. After sea ice, permafrost thawing is another response of Arctic environments to global change, both climatic and, as we will see, anthropogenic. Landscape changes associated with permafrost thaw are numerous, especially on the subarctic margins, where frost mounds are collapsing. Due to permafrost thawing induced by climate warming, they collapse and they are progressively replaced by thaw ponds, like here in subarctic Quebec, thaw ponds which are thermokarst features. Thermokarst subsidence is surveyed by, based on field monitoring and on remote sensing, and there are places like in South Sweden where the subsidence has affected 50% of some palsa fields since the 1950s. Thermokarst affected terrain has been also mapped, like you see on the slide, in Siberia. Same of the thaw lakes in the Barrow Peninsula in Alaska. And here, the interesting thing is that radiocarbon dating of organic material found in thaw depressions by Inkel's team showed that there were four different generations of thermokarst features, of which only a part is due to contemporary warming, whereas many others are inherited from past periods of climate warming. Of course, the rate of permafrost thaw highly depends on snow cover and vegetation changes. Regarding the vegetation, different landscape patterns associated with permafrost degradation have been described by Jorgensen and Osterkamp, and it has been shown for long, since the 70s, for instance, by Linnell, that the removal of the vegetation cover and of the insulating peat cover tremendously accelerates permafrost thawing. No doubt that there is a combination of natural and anthropogenic drivers involved in permafrost degradation and associated damages. Failures of pilings for buildings and pipelines are often attributed to global warming, but many human factors can contribute or even trigger permafrost degradation, such as soil mechanical disturbances, mismanagement, and poor maintenance in various Arctic countries, especially in Russia, but not only in Russia. But in Russia, the damages are particularly severe in cities like Yakutsk. In Russia, where predictive hazard mapping is being developed, here by Oleg Anisimov, based on permafrost models forced with climatic projections. They provide some general trends at wide regional scale, but the management of permafrost terrain at a local scale requires specific maps based on field investigations. A good example is provided by the mapping conducted in the Salouit village of Nunavik in Canada, which has known a rapid demographic growth, 30% within 10 years. And this village needs to find space to build 80 new dwellings. So combined with the geophysical soundings and sedimentological analysis, the mapping of all landforms and microforms indicative of terrain instability by Allard's team allowed the delineation of favorable ground for construction in ice-poor, coarse-grained soils and bedrock outcrops. Permafrost thaw induced by climate warming has also been described as an additional source of greenhouse gases, especially CH4, through the gas release from the thermokarst ponds and lakes. CH4 fluxes have been measured in various sites, like here in Siberia, in North Siberia, where hotspots of gas release are associated with thaw lakes, according to Walter's team. However, an integrated geoecological study conducted by Payet's team on the east coast of Hudson Bay showed that there is a concurrent development over decades of thermokarst ponds, which are a carbon source, and of peat accumulation, which is a carbon sink. So it seems that there is, over the decades, a compensation between the two processes, and this should be taken into account in when producing some emission scenarios. Of course, I would like to underline the particular sensitivity of some Arctic coastal regions, of which some are currently subject to accelerated erosion. Everybody knows the collapsing Shishmaref village in Alaska, of which inhabitants had to move to the mainland in 2002, for their houses were falling into the sea. An international research group, ACD, Arctic Coastal Dynamics, did a lot of work and provided rates of coastal erosion up to 20 meters per year along the Arctic coastline, with impressive mass movements like the ones described by Hugues Lantuy on the Yukon coast. Again, this accelerated erosion and associated damages must be attributed to a combination of natural and human factors. Natural factors are, of course, sea level rise, sea ice retreat, and permafrost thaw. But mechanical soil disturbances, especially in industrial zones, have undoubtedly exacerbated the erosion, as it was demonstrated by Ogorodov around an industrial complex of the Pechora Sea in Russia. After the sea ice retreat, after the permafrost thawing, let's have a look at what is very important, the continental glacier melting. Ah, c'est bien dommage. Sorry, I speak French. No, it's a pity, but I will describe what you cannot see. On Spitsbergen, which is an island halfway between the Arctic Circle and the North Pole, where the French geomorphologists have a station and have had this station for 50 years. The contemporary retreat of the glacial tongues should be obvious to you. So I describe. You can see one thing, which is the French base Jean Corbel, the French station. Imagine that above you have two glacial tongues which are retreating year after year. You had lines since the end of 19th century. You could see these glacial tongues retreating. And personally, I've been there 7 times between 1982 and 2004. And it was very easy to visually appreciate the glacial retreat. But much more impressive is the retreat of glacial tongues in Alaska, like this one, which underwent a 20-kilometer retreat within 60 years. It is a different story concerning the huge Greenland ice sheet, or at least the importance of the ice loss, if any, is vigorously debated. Many researchers point out the recent acceleration of the ice sheet outlets, like the one you see on the left, which provide the ocean with a large amount of huge icebergs, about from Greenland, some 15,000 icebergs are released every year. And based on satellite data, a scientific team provided the contrasting view of the Greenland ice sheet in 1992 and in 2002, showing in orange on the maps a pronounced increase of the melting calving zone, and inferring that Greenland ice loss makes a contribution to the sea level rise. As a consequence, in the following years, projections were published that predicted the almost complete collapse of the Greenland ice sheet. First, publication by 2000, by the end of the millennium, of the century, and finally they changed their projection, and it was reported even by IPCC that it could happen, but by the third millennium, not the end of this century. In contrast with this alarmist view, other scientists express a more optimistic opinion, indicating that you cannot take Greenland as a whole. It's the reason on the left. You can see that Greenland is divided into different parts. And to make it simple, the idea is that some parts of Greenland are stable due to climate cooling or even growing due to snow precipitation increase, and that the ice loss of the margins with all these icebergs is more than compensated by this ice growth in the inner part. But the debate is still open and is still vigorous. If you open the journal Science, every month or so you have something about the Greenland ice sheet. Well, whatever the health state of the Greenland ice sheet, glacial retreat is a reality in the Arctic as it is in the Alps, for instance, and there are some consequences on landscape dynamics. Wow. Well, I will explain what you cannot see. So during and following deglaciation periods, erosion is activated due to the abundance of meltwater and of loose debris deposited by glaciers. For instance, in some ice-cored moraines of Spitsbergen, the recent ice retreat resulted in the development of gullies and debris flows, which stopped to be active as soon as the dead ice content was exhausted. And in the same Arctic region on Spitsbergen, an older deglaciation period provoked the collapse of huge boulders due to the pressure release on debris-stressed slopes, increasing the rate of rock wall retreat. Yes, so you can see the glacial retreat on Spitsbergen. But, well, we were much, well, okay. So you can see the debris flows and the boulders collapsing from pressure release on debris-stressed slopes. And so it's a very important moment, the deglaciation period. And the geomorphic importance of deglaciation periods has been understood as early as 1971 and 72 by two UBC researchers, Mike Church and June Ryder, based on a comparison between active processes operating on Baffin Island and early Holocene alluvial deposits observed in British Columbia. It was formalized in an article on paraglacial sedimentation, which has become a classic, and the paraglacial concept was further refined by Mike Church and Olaf Slemaker in another benchmark paper published in 1989, and it's a great pleasure for me to have both Mike Church and Olaf Slemaker here. So based on this concept, what I called a paraglacial fever was triggered by Colin Ballantyne, a Scottish geomorphologist, who was followed by a French geomorphologist, Denis Mercier, who was a former PhD student of mine, and both had such an extensive view of what they called paraglacial geosystems are that every landscape compartment became periglacial, including coastal Aeolian landforms. Fortunately, a new paper, brilliant, thank you. Thank you. Fortunately, a new paper published last year by Olaf Slemaker in a special volume of the London Geological Society discusses in depth the significance and the relevance of the paraglacial concept. But it's interesting because we are talking about global change, and there was a kind of fashion effect in science around global change, and the way the paraglacial concept was developed recently is connected. It's a kind of a fashion effect in science, which is not the only one, but there are others. So the first consequence of glacial retreat was exacerbated erosion and removal, reworking of glacial sediments. The other one is, of course, that the deglaciated retreat, the deglaciated areas offer new potentialities for the flora and the fauna to colonize after glacial periods when plants and animals had been confined either on Arctic nunatak or in southern refugia. We have seen the restrictions to the fauna due to the sea ice retreat, but on land there is much more space for plants due to global warming, more space for plants and animals to colonize. Indeed, in some Arctic regions like Spitsbergen, the main threat to the flora and the fauna comes from human activity, such as soil disturbances provoked by hundreds and even thousands of tourists coming on shore. In some places like the Magdalena Fjord in northwest Spitsbergen, you see on the left, on top, severe restrictions had to be taken in order to allow the vegetation to recover. After trampling by the tourists, there had been really severe damage to the Arctic flora. While tundra vegetation is gaining space northwards due to climate warming, the boreal forest does the same. There is substantial evidence confirming the northward and upslope migration of the tree line in response to climate warming. More and more temperate vegetal species penetrate in the Arctic, as do bird species, although the higher Arctic remains the realm of the snow bunting. Of course, climate warming brings also new potentialities for agriculture development in subarctic regions, such as South Greenland, where vegetables such as potatoes, cauliflowers, cabbage, previously imported from Greenland, are grown now in Greenland. In the same time, new threats to the quality of grazing lands, for instance, in North Scandinavia, arise from pollution. It has been the case, especially following the Chernobyl catastrophe, which caused a big problem to the Lapps, to the Sami herders, in the following years because of the radioactivity trapped in the lichens, which were eaten by the reindeers, and the reindeer meat was too contaminated to be sold, and it causes socio-economic problems, especially in the 90s. So in the Arctic, you have both imported pollution with the chemicals transported from the south over long distances, which accumulate in Arctic food webs, and you have local pollutions with thousands of polluted sites which have been identified with less accurate data in North Russia, But in North Russia, some hotspots of pollution are well, sadly known, if I can say, especially in the highly industrialized Kola Peninsula and around the large metallurgical complex of north-central Siberia. Now I would like to share with you some ideas, some thoughts concerning projections and uncertainties related to the present and future, of course, of environmental changes in the Arctic, with some having wider implications. A first question, which is a general question for the whole world, deals with the appreciation of the current environmental changes. Are they unprecedented? Is it the very first time when mankind experiences these changes, when the Earth experiences these changes? Concerning the human impact, the answer is yes, of course. Demography and technology have never been so developed, and they have unprecedented environmental impacts. Concerning the climatic drivers, there is a vigorous debate, but I would answer no, most probably not. It's not unprecedented. The Holocene period has known two climatic optimums, one 6 millennia ago and another one millennium ago, which is attributed to a peak in solar activity. It is the little medieval optimum, which saw the Vikings sailing to America, including Ellesmere Island, because the sea ice retreat was very important. At that time, the Vikings settled in south and southwestern Greenland for more than 2 centuries. At that time, the boreal forest northern limit was 100 kilometers northwards of the present limit. And you know, I presume you know, that at that time there was very good wine produced in Britain, even north in Britain, and fig tree, olive tree in parts of Germany. So it was a very warm climate. It was the Middle Ages. It was the Viking Age. In the 1990 official climate change report, the IPCC report, the Viking optimum appeared clearly on the curve. You can see it in orange on the top right. It was a period of warmth, and which was followed by the Little Ice Age, a cold period in blue. And at that time, in 1990, the medieval climate was shown as more than 1.5 degrees warmer than the present climate. You can see on the right of the top graph that the contemporary warming appeared at that time in the IPCC report as much less than the medieval one. And below the first graph, you see another one, a red one, which appeared suddenly in the 2001 IPCC report, showing a completely different view of climate changes over the last millennium. So you see the red graph published by Michael Mann, which saw a very long and flat, almost flat, with a very little changes, temperature changes, covering what was previously the medieval optimum and the Little Ice Age. And suddenly you have a rise starting from the beginning of the 20th century and appearing as something completely unprecedented for the whole millennium. So two different ways to present the climate history over the last millennium. And this graph, the red one, was called the hockey stick graph, and its publication by IPCC as the one and only climate reconstruction triggered what was called the hockey stick controversy. I won't detail, but several climate scientists and statisticians said that man had used inappropriate statistical procedure for data processing, and on top of that, that his curve was too much based on climate proxies, which were not that reliable. In particular, the tree ring record was criticized. You know that the annual inside the trunk, the annual tree ring, their width depends on the climate conditions. And there was a long time when it was said that the warmer the weather was, the wider the tree ring was. And in fact, the tree rings, it doesn't mean that it's not useful, but there are two different informations in the tree rings. Informations about temperature, information about humidity. And if a tree ring, if the wood doesn't grow much, it can mean either that the weather is too cold, or that it's too dry, and it can be warm and dry. So there was some difficulties with the interpretation of the tree ring record, and as the curve, man's curve, had been too much based on this proxy, it's one more reason to criticize it. So a corrected curve, which might be not more correct, was provided based on the same data, and since then there has been many discussions and several scientists who provided additional curves we can see on the right, and again you can see the little medieval optimum and the Little Ice Age. There is now a view which is in between, before the first one and man's one, and there were many articles saying that the medieval optimum had been stolen, and suddenly, well, there is a kind of revival. What I mean is that if IPCC in this group, you have some people or some groups of people who are very powerful, and they provide a vision, their vision, and now after this, it was something of a mess, I mean, after the report, now there are different views which are offered, but what is important to us is it's that finally the medieval optimum, the fact that the Middle Ages climate was a bit warmer than ours, is again admitted. But, well, let's say that the debate continues. and will continue for some time, I am afraid. So you can see the problem. Some people say if the climate was warmer in the Middle Ages, probably it's not because we pollute the atmosphere that the present climate warming exists. So you can see the implications behind. So one can understand why it's difficult. But even the people who say that the medieval warming was higher than the present one, they just say, but in the same time, look at the results of the EPICA ice core. You have an overview of 800 millennia of climate history. You have data about the temperature change in red, and CO2 content changes in blue. And some people say, look, never during the 800,000 years you had such a concentration in CO2. So something happened. As there are connections, not connection, relationships, maybe not causal links, maybe it's much more complicated. But from the record, you can see that every time the temperature rises, it corresponds to a CO2 rise. So there is a wide community who say, look at this core, we never have had any such a high level of CO2 in the atmosphere. So something's going on. But again, others say, well, you compare the content, the atmospheric, the CO2 atmospheric content in bubbles, air bubbles trapped in the ice, to CO2 content you measure directly with instruments today. So again, the question of the comparison of methods used to obtain the results is a subject of discussion. For the future, of course, most of the models, climate models, predict the continuation of the warming trend. Climate models are based on different CO2 emission scenarios, and the predictions for the end of the century are somewhere between +1 and +3, maybe +4 degrees by the end of this century. To simulate future temperature trends, some models take into account not only the CO2 emission scenarios, but also the scenarios of Arctic sea ice loss, because, as you know, the dark ocean absorbs sun radiations, whereas the sea ice reflects radiations. So ice loss, more ice loss means more warming. It's a positive feedback effect. You have warming, it provokes sea ice loss, and you have an amplification of warming due to the fact that you have the ocean, liquid ocean, which is exposed. The future sea ice loss is predicted to be important, with some influential scientists predicting the total disappearance of summer ice around the North Pole by 2030. Before it was 2070, but since what happened at the beginning of the millennium, they consider that it is probable that in summer that there won't be any more sea ice over the North Pole. Permafrost 2 is predicted to undergo a severe reduction by the end of the century. It is thought to continue to move northwards in parallel to the advance of the boreal forest, according to the trends appearing in blue and green on this map, derived from a book published in 1993 by Hugh French and Olaf Slemaker about Canada's cold environments. And I heard that a new version is coming, so I will be interested in comparing the way you see the evolution now. As to the future sea level rise, it is also modeled according to different emission scenarios. Interestingly, as you can see on this graph, the current predictions, I mean, it's not predictions, it's, the current predictions are much less catastrophic than they were in the 1980s. The prediction is a few decimeters of sea level rise by 2100. We are very far from the catastrophic scenarios, like the one featured on this slide, for a main reason, which is contained in the book title. The book title, The Flooded Earth, well, subtitle, Our Future in a World Without Ice Cap. The main reason of this less alarmist view is precisely due to the reappraisal of the health state of the Antarctic ice sheet, which contains 90% of the total ice volume of the world, and of which melting would rise the sea level by 60 meters. So what is the idea about the health state of this huge ice sheet? Of course, some spectacular discharges of icebergs happen in West Antarctica, like the explosion, almost an explosion, of the Larsen ice shelf in 2002. But if most of the glaciers are retreating in West Antarctica, all of them don't. In 2001, I worked on Alexander Island, which is close to the peninsula, to the Antarctic Peninsula, and there is a sound which separates the island from the peninsula, George VI Sound, and currently it's full of ice. And there is geomorphic evidence that 2,000 years ago, the sound was ice-free. David Sugden, a Scottish geomorphologist, found shells, marine shells, which date back to 6 millennia, and I could observe geomorphic features, what we call honeycomb cliffs, honeycombed cliffs due to salt spray from the sea. So it meant that at that time the ocean was ice-free, at least seasonally, and now it is full of ice on a very thick, on a very important thickness, because it's not sea ice, it is continental ice coming from the peninsula. It's an ice shelf. But this, what I talked about, it was West Antarctica. But the big mass, what shall I do? Yes or no? Please tell me. No. No. Okay. Thank you. So now let's have a look at the East Antarctica, which is the most important ice mass of the world. Almost 5 kilometers thick. And several papers published in Science based on satellite data indicate that not only the East Antarctic ice sheet is stable, but it is slightly growing due to increasing snow precipitation. So what the conclusion is that the growth of the big mass of East Antarctica more, once again, than compensates the ice loss due to iceberg discharge. Even if they are very spectacular, the ice volume is not important compared to the growth of the inner part of Antarctica. So you see here the East Antarctica with the snow falling, and of course it becomes ice, and it's growing, and it's not a novelty. In the past, from ice cores and from also sedimentological evidence coming from the dry valleys, we know that during the interglacial periods, the Antarctic ice is more important than during the very cold and dry glacial periods. So it's nothing very new, and the Antarctic has been here for 13 million years. It's something which is very stable, I mean, in the world. Excuse me. There is some. Well, I will do it manually. Well, I said most of what I said was dealing with the warming trend, which is the mainstream. What most of the people say, at least the most influential people, but many people, and some others have a completely different view. Some predict and even already observe a cooling trend. They describe a cooling trend that would have begun either in 1998 or in 2002, that you can see No, sorry. And they say that we are at the beginning of a cooling period like the one we experienced in the 1950s and 60s. You can see the kind of plateau on the right between the temperature rise in the 30s and 40s. And you can see that it stopped. And in fact, in the newspapers at that time, it would be interesting to find them, but at least in France, in Europe, they were saying maybe a new ice age is coming. People were very unhappy about what was going on because it was cooling at that time. And as you can see from the graph on top, the problem is that it's difficult to say there is a cooling trend because of the interannual variability, which is very high. So it's not completely convincing. But other scientists, based on the geological record, predict that due to climate warming, which provokes massive injections of icebergs in the ocean, the surface waters won't be enough dense to sink to form deep waters offshore Greenland. And this formation of deep waters is very important because it is the starting point of the oceanic circulation. So if it stops, if the water, because of the icebergs, is not dense enough to sink, the oceanic circulation might stop, and you see what is the problem. It is this circulation which provides the north with tropical warmth, and it's an exchange, heat exchange between the tropics and the poles, and it would, for instance, stop the Gulf Stream, which brings warmth to Europe, of which climate would become colder. It has such a cooling is known from the marine geological record in the Atlantic Ocean. It has happened in the past during the Younger Dryas period, 11 millennia ago. So it's not completely fantasy. So I presume that now you measure what I call the ocean of uncertainties, which of course deserve further scientific investigation. The ocean of uncertainties is so important that there are even some scientists who bet some on warming, some on cooling. In the journal, famous journal Nature, in 2005, you had two Russians betting on cooling and one British on warming, $10,000 by 2030. So we will see what happens. Hopefully. Among the pendant questions are those related to the mass balance of the Greenland ice sheet. Does the ice loss on the margins contribute significantly to the sea level rise, or does the growth of the inner part more than compensate this loss? Well, we don't know right now. Uncertainties, too, concerning the dynamic behavior of the Antarctic ice sheet, because since the collapse of the Larsen ice sheet in the peninsula, Now the researchers pay a particular attention to the other Antarctic ice shelves, of which some are thinning due to ocean warming. And they pay a particular attention to the ice shelves in red and blue, with the black circle on the map, because these two ice shelves are the main breaks of the Antarctic ice sheet. If they start to collapse, it might trigger an acceleration of the ice streams behind, and it would drain the Antarctic ice sheet with a dramatic sea level rise. So there are many programs to monitor the ice sheet changes based on satellite data, but also based on the field studies. In both the Arctic and Antarctic regions, a network of scientific stations is being developed to monitor the current environmental changes based on standardized protocols, like the one developed in Antarctica by our Japanese colleague Norikazu Matsuoka. And if some of you are interested in geomorphology, and if you wish to know more about what's going on in the Arctic, you can have a look at the book I mentioned when I began, edited by Olaf Slemaker, Geomorphology and Global Environmental Change. Thank you very much for your attention.
Thank you very much, Marie-Françoise. Are there questions? Yes, please.
I'm curious what your own greatest personal uncertainties are from your own research about the debate about climate warming and the kind of impacts, whether it's happening or not, and what kind of impacts it will have.
Well, one thing which bothers me, it's not directly connected with my own research, but it is the CO2, the comparability of the CO2 content of the present atmosphere and the content which is known from the air bubbles in ice. Is it really possible to compare it? Isn't it possible? I discussed with the glaciologists and paleoclimatologists. They said to me that they make some kinds of corrections, because you imagine you measure now in this room the CO2 content, air content. Well, you have at a given time a value. Then you go inside the Antarctic ice sheets. You know how it forms. You have snow with much air inside, and there is a compaction. So the air bubble, they merge, and there is a kind of average concerning the content, the CO2 content. Well, it's one thing. And the other thing, and it's something I am not able to solve, it's exactly what are or what are not the causal links, because everybody shows these curves parallel. You have temperature, you have CO2, and so, of course, they say they go together, but is the temperature the cause of or the other, or is something completely different, driven with vegetation, with ocean. I mean, the Earth complex is complex. You have glaciers, ocean, atmosphere, vegetation. And so we don't, at this moment, we don't completely understand what's going on and how the different processes interact. And so I'm curious.
Yes, please.
What is the position of the National Academy of Sciences in France as to whether we're entering a period of global warming or global cooling?
Well, I think as far as I know, the Academy of Sciences in France won't say there is a cooling. At the moment, when they publish reports, it's not it's not exactly on the IPCC line, but I mean it follows the main trend. It's climate warming. I mean the question of the cooling is not now in France much presented right now.
Well, I think people are exhausted. I must congratulate you on recovering so much more gracefully than the previous speaker did at his disastrous slide presentation. It's a pleasure to thank you, Marie-Françoise, and we look forward to subsequent presentations in this series, and thank you for coming, and we appreciate this extraordinary and well-illustrated presentation of the range of problems. I think the emphasis on uncertainties is certainly something very salutary at a time when people are celebrating what they think is the solution, and that the effects of global warming have been adequately identified, and more particularly that the mechanisms that have caused global warming have been satisfactorily identified. So many of these issues are just now entering into the critical debate phase. And I think this is the very interesting stage in the evolution of our understanding. So thank you very much.
And thank you to everybody.